A robot video goes viral because it appears to learn on its own, seemingly evolving from a clumsy prototype into an efficient machine in real time. The harder question asks what had to work physically for that evolution to happen at all. Today, we unpack the mechanical story behind self-destructive learning and why turning failure into data is one of the hardest engineering challenges in modern automation. The prevailing narrative suggests that artificial intelligence simply absorbs experience, treating every stumble as a gentle correction. In reality, the gap between simulation and physical deployment is defined by something far more brutal: the conversion of failure data into mechanical action through kinematic self-destruction. This process relies on an autoregressive sequence model trained in simulation to identify components hindering performance and actively remove them. The robot does not just adjust its software, it physically thrashes redundant links against surfaces until they detach, effectively sculpting its own body to optimize locomotion for unseen environments. This approach represents a fundamental shift in how we view the feedback loop between intelligence and hardware. For years, engineers have struggled with the sim-to-real gap, where policies that work perfectly in virtual worlds fail catastrophically when applied to physical systems. The solution here is not just better sensors or more data. It is an inverted reward function. Instead of seeking stability, the system learns to actively seek out and execute the physical removal of components that hinder task performance. In this scenario, the robot's body becomes a dynamic hyperparameter, evolving through irreversible structural loss rather than temporary adjustments. The core engineering constraint driving this shift lies in distinguishing between useful failure and catastrophic collapse using only internal joint torque and position data. A robot must navigate a narrow path where it identifies redundant links causing inefficiency without triggering a total structural disintegration. This requires a proprioceptive signal-to-noise ratio that is incredibly difficult to achieve, as the machine cannot rely on external ground truth or visual confirmation of its own state during these destructive episodes. It must infer from the resistance in its joints whether removing a specific link will lead to smoother movement or cause it to fall apart entirely. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To make this viable, researchers have introduced techniques like morphological wobbling. This serves as a critical regularization method that forces the robot to learn invariant control policies capable of generalizing across physical perturbations rather than overfitting to a specific static configuration. By oscillating mass and actuator strength during training, the system develops robustness against instability without requiring permanent structural damage in every instance. However, when the simulation proves out, the transition to real-world deployment reveals that reductive, destructive actions can be a more efficient learning signal for certain tasks than maintaining a stable form throughout the process. The success of this strategy is measured by its ability to generalize morphologies and transfer control policies directly from virtual training to physical hardware with superior forward movement compared to random removal policies. When tested against unseen configurations, robots utilizing these self-destruction protocols demonstrated enhanced adaptability in unanticipated environments where traditional methods would have stalled. The system effectively turned the robot's body into a dynamic variable, allowing it to find solutions that no human engineer could have pre-programmed for such specific failure modes. However, this feedback loop introduces critical production trade-offs that define the current limits of industrial adoption. Because self-destruction is irreversible, the robot cannot recover from a failed design choice once a component has been torn away in the real world. This demands simulation environments with extreme fidelity to model material fracture and joint failure physics before any physical deployment occurs. If the virtual environment underestimates the strength of a connection or overestimates the torque required for detachment, the learning process can destroy the hardware permanently rather than refining it. The computational cost of training models to predict these structural failure modes with high fidelity remains a significant barrier. The system must accurately simulate how materials break and joints separate in real time, while simultaneously optimizing control policies for locomotion. This dual requirement creates a complex optimization problem where the robot learns both how to move efficiently and when it is safe to destroy parts of itself. Until simulation environments can reliably predict these outcomes without prohibitive compute costs, widespread adoption in safety, critical, or high-reliability industrial settings remains limited by the fear of permanent structural loss during the learning phase. Furthermore, while benchmark results show enhanced adaptability, the long-term durability of repeatedly thrashed joints presents an unresolved question for mass deployment. The mechanical wear and tear accumulated through active self-destruction may compromise the lifespan of actuators and structural links faster than traditional training methods that preserve hardware integrity. Engineers must now balance the efficiency gains from adaptive morphologies against the economic reality of replacing worn-out components more frequently due to their role in the learning process itself. Ultimately, this technology challenges the assumption that intelligent machines must remain static during operation or rely solely on software updates for adaptation. By proving that reductive actions can serve as a valid and powerful learning signal, we see a future where robots evolve physically alongside their intelligence. Yet, until the simulation-to-reality gap in fracture physics is fully bridged, this method remains a high-stakes tool reserved for applications where adaptability outweighs the risk of permanent structural degradation. The path to truly autonomous systems will likely involve a hybrid approach, combining the sculpting power of self-destruction with the safety margins provided by morphological wobbling and robust simulation fidelity. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.